Got all this stuff up and running now. So today, we're going to pick up where we left off last time. So we were talking about polynomials last time. And of course, yes. And we had been talking about just kind of some basic definition about like what do we mean by a polynomial. So we had said a polynomial is just the sum or difference of monomials. And we had said that a monomial is, like a real number multiplied to a variable with a non-negative whole number exponent. Right? Some examples of things that were monomials and were not monomials. So, for example, 3x squared is a monomial, but 5x1 is not. The reason it's not is because the exponent is not positive, or not, isn't non-negative. In that case, it's negative. 10x to 1/2 is not a monomial. Its exponent isn't a whole number. 3 over x is not a monomial because the x is in the denominator. Although x over 3, think about that as like 1/3 x to the first. So x's in the numerator of a fraction are okay, but you can't have x's in the denominator. And then say like something like this is not a monomial because the exponent is in the exponent, or the exponent is a variable, not a non-negative whole number. So just some quick examples of things that are monomials and aren't monomials. Does that all kind of ring a bell? And I think that's about where we had left off, right? So a polynomial is just going to be the sum or difference of a bunch of monomials. And we had said that a single monomial is still technically a polynomial. You should always think about the single monomial plus 0, since a real number by itself is a monomial. So let's do a little bit more vocab. So let's say that we have the monomial 7x to the third. So that number in front of our variable we call the coefficient. And the number in the exponent we're going to call the degree of the monomial. So for this monomial, its coefficient is 7 and its degree is 3. Everybody okay with that idea? Now remember, a polynomial is going to be the sum or difference of several monomials. Oops. Let's do that. So this is an example of a polynomial, right? We just have 4 monomials that are being either added or subtracted. Maybe turn off our videos and pay attention to what's going on. So this polynomial has 4 coefficients. Again, the coefficients are the numbers in front of the variables. Now there's one coefficient that's of special interest to us. And we'll come back and talk about how we can identify that coefficient in a moment. When we talk about the degree of a polynomial, though, which exponent are we talking about? It's not all of them. It's just the biggest. Is everybody okay with that? And the coefficient on the monomial that has the biggest exponent we refer to as the leading coefficient. Everybody okay with that idea? And each of these monomials are what we refer to as a term. So each of these monomials is a term. So this polynomial has 4 terms. Is everybody okay there? And one of these terms in particular is of special interest to us. This one at the end is called constant term. Because it has no variable attached to it. It's just a coefficient. Any questions right now about this vocab? So we haven't really done anything yet. We just kind of building up some language so we can talk about polynomials a little bit. Let's do an example where we just kind of practice that vocab here. Okay? Just to kind of make sure we got it. Okay. So let's ask a bunch of questions here. Okay. So we're going to ask 4 questions here. I'm going to ask you, how many terms does this polynomial have? What do you guys think? 4, right? Everybody agree with that? Okay. So we have 1, 2, 3, 4. What is our leading coefficient? Enzo? Sure. What would our leading coefficient be here? Close.
Oh, no, 7.
It's negative 12. Why negative? Because the subtraction symbol in front of it is technically attached to the 12. Is everybody okay with that? So again, we're looking at for the leading coefficient, you find the term with the biggest exponent, and that's the coefficient that you want. What's the degree here? Connor, 5 is correct. Again, you're just finding the biggest degree term. And then here's the tricky one. What's the constant term? There is a constant term here, because what can we always write added to the end here? You could always write in a plus 0, right? So the constant term here in this case, since there isn't anything with no variable attached to it, is just 0. Joe?
I just have like a general question about monomials.
Sure.
So the coefficient, it doesn't matter if it's negative or positive, right? For monomials.
The coefficient could be negative or positive, right? That's fine. Yep.
But the exponent has to be a non-negative whole number.
Correct.
Okay. Thank you.
You're welcome. Everybody feels okay about this with the vocab here? Okay. So we have 2 major ways to classify polynomials. Oops. So the first method is by degree. So if the degree is 0, we call that a constant polynomial. So for example, 7 is a constant polynomial. If the degree is 1, we call that a linear polynomial. So for example, negative 3x would be a linear polynomial. Or even if I had negative 3x plus 5 is still a linear polynomial, right? Again, the degree for the polynomial is just the biggest exponent. Are we still okay with that? If it's a degree 2, we call this a quadratic polynomial. So for example, negative 5x squared, or you could have like negative 5x squared plus 3x, or you could have something like negative 5x squared plus 3x minus 10. All of those are quadratic. Scroll that up a little bit. You still feel okay with the vocab here? So we're just kind of describing some different names that we give these things. If the degree is 3, we call that a cubic polynomial. So for example, you could have 6x cubed or 6x cubed minus 5x, or like 6x cubed plus 4x squared minus 5x, yada, yada, yada. Right, there's lots of, but you get the idea, right? There's getting to be too many combinations for me to write them out. It just becomes a hassle. You get what I mean, right? If you have a question, for sure, I'd love to clarify if anything comes up, but we're just basically given some names here. Degree 4s are called quartic polynomials. So like 10x to the 4th or 10x to the 4th minus 7x cubed plus 6. You know. Your yada, yada, yada. And that's about as far as I would expect you to know the names for. I mean, there's names for bigger ones, but any bigger than that, let's say degree n, where n is greater than 4, we just call that a degree n polynomial. So rather than having a fancy name for it, we'll just call it, name it by its degree. So for example, 3x to the 7th, we just call it a degree 7 polynomial. Everybody okay with that? So once you get past 4, nobody, at least I'm not going to worry about having the proper name for anything. You can just call it by its degree and we'll all know what we're talking about. The second way we classify our polynomials is by the number of terms. So if there's one term, we just call that a monomial. Two terms, we call that a binomial. 3 terms, we call it a trinomial. And that's as far as I would need you to go. So if we have n terms where n is bigger than 3, we'll just call that a polynomial. And we're not going to worry about the prefixes there. Okay with that? So oftentimes, we're going to want to name the polynomial in both methods. So for example, if we have 7x squared plus 3x plus 5, we note that this is, the degree here is what? For this polynomial, what's the degree? 2. And the number of terms is?
2.
So we'd say that this is a quadratic trinomial. So oftentimes we're going to use both classifications when we name or talk about our polynomial. Let's do another example. Sound good? We'll just do a couple to make sure that we have these naming conventions down. Just not that I am going to require you to do a lot with it, but it's important that, like, if I'm talking about something, you guys are able to understand what it is that I'm saying, right? When I start using the vocabulary. Okay, so let's say we're looking at 5x cubed plus 5x. The degree here is? Good. And the number of terms is? 2. So we'd call this a cube binomial, right? Where the number of terms gives us the second part and the degree gives us the first part. And when we talk about these things, we always name it in that order. We do the degree part first and the number of terms part second. Is everybody okay with that? Okay. So the focus for this next chapter is going to be on quadratic polynomials. And after we finish chapter 4, we'll talk about bigger polynomials than in general and how to deal with some of those. But usually, it's not uncommon in mathematics to look at a simpler situation before we extend that out to a more complicated or more general one. Rather than starting with the most general and working to the specific, oftentimes we work in a specific situation to get a feel for what's going on and then try to extend it to the more complicated, more general situation, which is what we're going to do here with chapters 4 and 5. So everything we're doing in chapter 4 is still going to apply inside of chapter 5, but not all the time, right? So in chapter 5, we'll still talk about quadratics. We'll still use a lot of the techniques that we develop here in chapter 4 when we run into quadratic polynomials. But all the techniques we built here in chapter 4 wouldn't work necessarily on, say, a cubic polynomial, right? So we have to, be a little bit careful there with that. But that's the relationship here between chapters 4 and 5, is that they're quite closely related. Okay? So remember that when we talked about absolute value functions, we talked about there being like 4 major skills that we like to worry about. Inside of each of these chapters where we talk about a function. So those 4 skills were simplifying, graphing, solving, and modeling in some order. I don't remember the order that I quoted last time, but again, inside of this chapter, these are going to be the 4 major skills that we're going to be interested in. So we're going to start here today with the simplifying skill. So when we talk about quadratic polynomials, there are really 3 ways or three forms, let's say, that we use to represent them. The first one is called standard form. So standard form is written ax squared plus bx plus c, where a, b, and c are the coefficients. So for example, 7x squared plus 3x minus 5 is a quadratic polynomial written in standard form. What is the coefficient that represents a? 7. And the coefficient represented b? 3. And for c? Negative 5. Is everybody okay with that? What if instead we had written this? Is this written in standard form? Technically, no. What's wrong with it? The terms are written in the wrong order, right? So what would we need to, how would we rewrite this so that it is in standard form? So we do negative 3x squared plus 6x plus 10. Is everybody okay with that? So again, now we can see the value for a, the a coefficient would be negative 3. And the value for the b coefficient is 6. And the value for the c coefficient is 10. So again, the takeaway here that what I'm trying to get at is that value for the a coefficient is the coefficient on the x squared, not necessarily the first coefficient in order. Is everybody okay with that? And so on and so forth for b and c too, right? You have to write it in order before you can pick out the a, b, and c. Or you have to pick out the a, b, and c looking at it in the standard order. Does that make sense? Okay. We feel okay with standard form? All right. The next one is called factored form, or sometimes we'll call this intercept form. We'll talk about why that we might call it that later. So intercept or factored form is a times the quantity x minus p times the quantity x minus q, where the a, p, and q are just constants. They're just like real numbers. They're not variables. So for example, if we had 3x minus 2 times x minus 5, is this in factored form? Yeah, right? So what would the value for A, P, and Q be for this polynomial? Our value for A is 3. Our value for P, be careful here, so it's positive 2, because look at the formula. The general form has a minus sign in it already. So if I put a negative 2 in for P, I'd have x minus a negative 2. So really our value for P here is just 2. Is that okay? And we saw something similar to this with the absolute values for the value for h, right? H was always the opposite sign of what it appeared in the formula. The same thing is happening here for the p's and q's. So what's our value for q? 5. Do we feel okay with that? Okay, let's do one more example. Is this in factored form? Not quite, right? What's wrong with it? If I look at the general form, I have to have x's with no coefficients on them. Here, one of my x's has a coefficient on it. Do you guys see that? Is there a way that we can fix that? Connor? Right. So really what we're going to do is we're going to take a greatest common factor from that first quantity. So that greatest common factor that we can take out is 2. And to find the new resulting quantity there, we're going to divide everything in that first parenthesis by 2. So 2x divided by 2 is x, and 4 divided by 2 is 4, and then the other parenthesis remains unchanged. Is everybody okay with that? Again, taking a greatest common factor off is something that you should remember from your Algebra 1 class. That should have been, or pre-algebra even, you should have practiced that skill quite a bit. An easy way to check to make sure you've done that correctly is if you distribute that 2 back through, you should have the same thing that you started with. Okay. So what is our value for A, for P, and for Q in this one? A is 2, good. P is negative 2, and Q is negative 2 also. Does that feel okay there, guys? Good. All right. Our third representation is called Vertex Form. And what this looks like is A times the quantity x minus h, quantity squared, plus k, where A, h, and k are constants. So an example of a quadratic polynomial written here in this vertex form could be negative 3 times the quantity x minus 1, quantity squared, plus 2. So our value for a in this case is -3. And our value for h is +1. Very good. And for k, it's +2. Does everybody feel okay with that? Good. So the first thing that we're going to worry about is how to translate back and forth between these three forms. So the way this is going to work so we have intercept form, standard form, and vertex form are the three forms. So I've just abbreviated those with their initials. So intercept form or factored form and is IF. Standard form is SF. And vertex form is VF. So to go from intercept form to standard form, what we do is FOIL. So let's look at an example of that. Actually, let's fill this in and then we'll do some examples. To go from vertex form to standard form, we're going to expand and then distribute. We'll explain what we mean by some of these things and develop these techniques and do some examples on how to do this. Some of these a lot, because some of the techniques will be brand new. Some of them just a little bit, because they're kind of techniques that we already should know about or should look familiar. To go from standard form to intercept form, we have to factor. And to go from standard form to vertex form, we're going to use a process called completing the square. I just abbreviate this as CTS because that's a lot of words. So this is like our roadmap for moving in between these three forms. So we'll refer to this quite a bit here in this first, when we talk about these simplifying topics. But it's going to be important to us that we're able to translate back and forth between these forms, because it makes doing certain kind of problems massively easier if you're in one form versus another. So this will become very important for us when we talk about graphing or solving a little later on, that we're able to do this effectively. Okay? So let's look at some examples. So the first place we'll start is just going from intercept form to standard form. So we'll just do some examples of doing this to start with. Okay? So if you guys look above, we wrote FOIL as the direction. And if you remember from your Algebra 1 class, FOIL stands for first, outer, inner, last, So it's like an acronym or whatever. And it's just describing to us how we multiply two things that are in parentheses together. So it starts by multiplying the first thing in each parenthesis together. So x times x is x squared. Remember, when you multiply two variables together, the exponent changes. And then the inner, so we'll multiply the stuff on the insides of the parentheses. So 3 times x is just 3x. Everybody's okay with that? And then we have the outers. So that's the stuff in the outside most part of the parentheses. So x times -5 is -5x. And then we have the lasts. So the lasts, which is the last two things in the parentheses. So 3 times -5 is -15. And then we just need to combine our like terms. So you notice in the middle here, 3x and -5x can be combined together because they're both like terms. They're both x to the first power. And we can combine those like terms by just basically looking at the coefficients. So 3 minus 5 is -2. So 3x minus 5x becomes -2. Is everybody okay here? Do we remember foiling from our Algebra 1 class? If we didn't, hopefully this example kind of brought that tumbling back for us. It's a relatively easy skill, but no sense in not reviewing it then, right? Making sure that we still have it. Yes, Tyler. Of course. So again, here's another intercept form. And this one's a little bit different because we have this -2 out front, right? So what are we going to do with that -2? Well, here's the trick. If you remember back from your Algebra 1 class, if you have three things that are multiplied together, it doesn't matter what pair of things you multiply together first, as long as you remember to end up multiplying all three things together in the end. So we have some options here. We could do -2 times the x minus 3, and then take that answer and multiply it by the x plus 6. Or we could multiply the x minus 3 and the x plus 6 together, and take that answer and multiply it by the -2. Either option is okay. What I typically like to do is this one, is I tend to make less mistakes there. I think the foiling is easier as long as the numbers are small. If I multiply the -2 in first, it makes the numbers a little bit bigger immediately, and I think it makes the foiling a little bit more tedious. But either of those is okay. Is everybody okay with that? As an aside here, what we don't want to do, that I see students do quite commonly, is they do this and multiply the -2 to both sets of parentheses. That's bad. That's not correct. Do not do that. Is everybody okay there? We see why it's bad? This would be equivalent to saying if you had 2 times 3 times 5, saying, oh, what I do is I do 2 times 3, and then I do 2 times 5, and then I multiply those together. Right? Like you wouldn't do that. You just do 2 times 5, or 2 times 3 is 6, and then 6 times 5 is 30. You wouldn't do that. That'd be the equivalent of what you'd be doing there, which again, you put the variables in the parentheses and it gets kind of confusing looking, and you do things that you make up stuff that's like, you wouldn't do that if they were just numbers. You try to remind yourself that again, like that parenthesis is just kind of the same thing as one number. If you treat it like that, it kind of prevents you from doing silly things, mistakes you wouldn't make if it was just like whole number arithmetic. Is that okay? Okay, so let's do this multiplication now, as we've talked a little bit about what not to do. And since I'm the one doing this, I like doing it the way that I circled here in yellow, as opposed to the other way. But the other way is still fine if you like doing that. It's no big deal. So I'm going to have my -2, and then my FOIL. So the first, I get x squared. The outer, I get 6x. The inner, I get -3x. And the last, I get -18. Is everybody okay with that? I'll combine my like terms. So 6x minus 3x is just 3x. And then I will finish by just distributing that -2 through my parenthesis. And there's my final answer. So if you think about this, this is really the same process that we did on the previous example. We just had one more additional step at the end where we distribute that coefficient through whatever we just FOILed out, right? Which I think is the easiest way of thinking about it for me. But again, like you can try it a couple of different, try it both ways and see which one you like. They're both doing the same thing. And there's certainly situations where I might do one versus the other because it makes the arithmetic a little easier. But in general, this is kind of where I start at, or where I like to start at. Do we feel okay about foiling? Hopefully that seems pretty familiar, right? Okay. My next example I want to do is going from vertex form to standard form. And we said that this was expand and distribute. Oops. That wasn't very readable. Okay, so here's our example. What we mean by expand, because that's the word in there that we're probably not familiar with. Expand refers to how I deal with this piece right here. So recall for a moment that we know that x squared is, say, the same thing as x times x, right? Everybody's okay with that? So what we'll do is think of x plus 2 squared as just x plus 2 times x plus 2. Everybody's okay with that idea? So now we can just FOIL, right? You take that first part, and we'll just treat it like one of the previous problems that we did. So x times x is x squared. X times 2 is 2x. 2 times x is 2x. And 2 times 2 is 4. So far, so good? Now we'll distribute that. Oh, let's combine the like terms, I guess. So 2x and 2x is 4x. And then we'll distribute the 5 through. And then we can subtract the 6 from the 20. And there's my result. So not much different than the other one, right? We just have to take that squared term and rewrite it as a FOIL problem. And then we just FOIL and do some combining of like terms at the end. But not too bad. Let's do one more just to kind of make sure we get it. Before that, though, I want to make sure I point this out. Every year I see lots of students doing this, saying x plus the quantity x plus 2 squared is just x squared plus 2 squared. That is very bad. Don't do that. That's almost never true. You have to FOIL, like we did here. Joe? Of course. Okay. So again, I like to point out these common mistakes that I see students make, just so if you're thinking like, why can't I just do that? I want to make sure before you think about doing it, I'm telling you like, don't do that. It's not correct. And again, like, you know, lots of experience tells me that these are things that students end up trying at some point or another. So I'm just trying to answer that question before it comes up in the homework or whatever. Okay. So again, we're trying to write this in standard form. So the first thing we'll do is we'll expand. We'll rewrite x minus 5 squared is x minus 5 times x minus 5. And then we'll FOIL this out. And I'll pause here and let everybody kind of catch up, as I know I was writing a little bit fast. Okay. I'll combine my like terms inside that parenthesis. So negative 5x minus 5x is negative 10x. Then I'll distribute my negative 3. And then I'll combine my negative 75 and negative 25 to get negative 100. So we feel okay here. So again, these first two skills that we've talked about here today should feel pretty familiar, should feel relatively comfortable. You should be thinking, this is not so bad, right? Pretty easy. At least in comparison to some of the things that we've done already this year. This is pretty easy. The next one that we're going to work on is going to be going from standard form to intercept form. And to do that, we said the instruction was to factor. We're going to spend the rest of today kind of setting up how to do this factoring skill. And we're going to take another day this week just kind of practicing this factor skill. Of all the things that we learn in first semester, the ability to effectively and quickly factor a quadratic polynomial is maybe the most important thing we do in first semester. So I'm willing to take like an entire day just to spend in class practicing to make sure that we have an opportunity to do this and to get things checked and to make sure that we can do this, because it is a really important skill moving forward that'll become an issue not only in the rest of this year, but in future classes if you're unable to do this effectively. Yes? I'm sorry, you mumbled. Yes, go ahead. So I just want to kind of set this up that this is, you know, a rather important skill here, okay? Mostly because it's a really transferable skill that a lot of more complicated problems that we'll see later on kind of turn into quadratics or end up turning into a quadratic. And the ability to factor is going to be very important for us able, you know, to solve a quadratic or to simplify other more difficult problems later on. So this is a really important skill. So to kind of set this up before we do an example, so I'm going to take a little bit of give a little bit of background and kind of discuss what it is we're trying to do and how to do that and what we need in our process in order to do that before we get going into the example, just so it's a little bit more clear as to why I need to answer these questions or why these questions are giving me what I need to get my answer, or so on and so forth, okay? So the idea is that factoring is the reverse of FOIL. So that's what we're basically doing, is the reverse of FOIL. So let's look at a quick example here. Of a FOIL problem and talk about what it would look like to move backwards from that. Okay? So to do that, we're going to get x squared and then x minus, or x times negative 5x, or negative 5, and then plus 3x minus 15. And then we combined our like terms to get us to here. Okay. So this side was our FOIL. And then over here, we're going to kind of do our factor. Maybe I should, let me do it like this. I'll write it here. Okay. So we're going to start with a standard form polynomial, which is this, and we want to end up in the factored form, right? So the most difficult step is this one right here. So what would we have to do in this, moving backwards this step? What we have to figure out is how to break negative 2x up into negative 5x plus 3x. Is everybody okay with that? Right? We see that that's the change that we made, so that's what we have to reverse on our first step to factor. Right? We're trying to undo factoring. We're moving backwards, so that was the combining of like terms step that we did when we FOILed. That's the last thing we did when we FOILed. It's the first thing we have to do, or undo when we're factoring, is to undo this combining of like terms. The way we do this is we need to answer the question, what two numbers multiply to give C and add to give B. Oops. Let's actually say AC. So what do I mean by A, B, and C here? I'm talking about the coefficients from our standard form polynomial. So if we look at our standard form polynomial, what is our values for A, B, and C? What does A equal? So again, this is our starting problem right here. This is our standard form polynomial. A is 1. Very good. Remember, there's always a 1 in front of any variable if there's no number already written there. What's our value for B? Careful. Negative 2. Very good. And our value for C is negative 15. Everybody okay with that? So what I need to do then is I need to find two numbers. I'm going to call those numbers M and N. They need to multiply to give me 1 times negative 15, or negative 15, and also add to give me negative 2. Everybody's okay with that? The easiest way to do this is by guess and check. So the problem that we're going to start with is always going to be with the multiplication problem. And we're just going to start by writing down the numbers that can multiply to give us negative 15. And each time we're going to check those to see if they can also add to give us negative 2. Why do we want to start with the multiplication problem? Because there's only finitely many pairs of whole numbers that can multiply to give me negative 15. I don't want to start with the addition problem because there's infinitely many pairs of numbers that can add to give me -2. Right? -2 and 0, -3 and 1, -4 and +2, and going on and on. And you can do that forever, and it's a mess. Right? We always want to start with the multiplication problem. So numbers that multiply to give me -15, well, there's 1 in -15, but those don't add to give me -2. There's -1 in +15, but those don't add to give me -2. There is 3 and -5, and that's the pair that I need. Is everybody okay with that? So what that allows me to do then is I can write x squared plus 3x -5x minus 15. And if we look, that's exactly what we have here, except the 3x and the -5x are written in a different order, but that's fine. It's no big deal. Does everybody see that? Okay. So the next trick here, what I'm going to do next is called factor by grouping. And that's what's going to allow me to move from the middle step back to the factored form. Okay with that plan? I haven't told you how to do factor by grouping yet. I'm just telling you what it's going to accomplish. So again, remember we're moving backwards through FOIL. I'm going agonizingly slow in doing this intentionally, because it's a really important skill and I want you to understand why this process works. And in the next lesson, we'll streamline this so it doesn't take like 15 minutes to do. It'll be something that we can do in our head almost, or should be able to do in our head eventually. But it'll do a little bit of streamlining. But it's important we understand what it is we're trying to accomplish and how we're doing that before I just get you a mystery process that's like a black box that somehow gets an answer. Okay, so the idea here with factoring by grouping is I'm going to make two groups. Between my two groups, there's always got to be a plus sign. Is everybody okay with that? I can always make my two groups just the first two things and the second two things. That's always going to be fine as long as there's a plus sign in the middle. Mr. Kulik, what would I do if there's not a plus sign in the middle? What if I had a subtraction symbol there? Just rewrite the subtraction as plus and negative. Like we did here, right? I could have written that as 3x minus 5x, but I just wrote it as plus and negative. Is that okay? All right. From the first group, I'm going to look for a greatest common factor. What is in common between x squared and 3x? Is there a factor in common between x squared and 3x? X, right? Everybody agree with that? So if I factor an x out, I'd have left x plus 3. Is everybody okay with that? You see that? Yes? Okay. And then I'll look at the second group. Is there a common factor between negative 5x and negative 15? Yeah, what is it? Negative 5, right? Everybody agree with that? So when I factor the negative 5 out, negative 5x divided by negative 5 is just x. Negative 15 divided by negative 5 is positive 3. Everybody agree with that? Now what I'm going to do is I'm going to look at this as one term and this as one term. Is there anything in common between each of these? Yes. It is the x plus 3. Everybody agree with that? So when I factor the x plus 3 off of the first one, I have just x left. And when I factor the x plus 3 off the second piece, I have just minus 5 left. And you'll notice that now I have exactly what I started. Is everybody okay with that? We're going to stop here. I'm not going to have an assignment here for you guys yet. I want to take some more time in class and talk about this some more. And we'll deal with it on Wednesday. But hopefully so far things are going okay. We'll do a lot more with factoring on Wednesday again. So if you're not quite sure what I just did here, that's okay. We'll do it again on Wednesday, and we'll do some more examples and give you some time in class to work on some things. But nothing for you guys to work on at home tonight. Okay? Very good.